We're going to start the introduction to inverters and converters. The inverter is a simple difference. It is used to convert DC voltage into AC voltage to be used by the electric motors. Now, the converter is a power conversion of DC to DC. It can be from low voltage DC to high voltage DC, from high voltage DC back down to low voltage. But it's a small difference. Converter converts one level to another. An inverter actually turns it into an AC voltage. Now, the motor generators, the traction motor and the generators, are going to be using this AC voltage to operate, and it's important. The electronic components to accomplish the same thing the ICE does, but it's going to have less components and with greater torque at startup and equal torque at the road. We're going to talk a lot about torque because married to this is going to be motors. So we'll get into that in a moment. So here we have a drive motor on the left and a battery pack on the right. Now we've got to put all the electronics together to make this work. First of all, we've eliminated an alternator because if we're driving with an electric motor in a full hybrid, we're not going to be turning the internal combustion engine or the ICE. So we're going to have something to replace the alternator. The DC to DC converter replaces the alternator, gives us 14 volts to charge the battery, and all of this is going to happen under control of a battery pack controller. It's going to make sure the battery's never overcharged in the high voltage battery pack, the temperature's right. Now all of this electronics has got to hook together with a drive motor controller. We're going to have electronics smart enough to control this motor. The way it does it is through the power inverter. The power inverter down here receives power from the battery pack and controls from the drive motor controller. They're usually housed in the same thing. This is very critical, and we're going to show you as we go through this. But the drive motor itself is going to have no brushes, meaning it's permanent magnet. Now we're talking about running over 100 amps in many cases. If we're over 100 amps, we could not possibly tolerate carbon brushes like we do on a small little DC motor for the fuel pump. Wouldn't work. Current's too high. The shape, the length, the width, and thickness of the magnets in this permanent magnet motor will vary depending on the torque and RPM requirements. Large, heavy magnets do not have high RPM capabilities. Strong magnets, and we'll demonstrate them to you sometimes, have high torque in small packages. New rare earth magnets are very effective for motor design. And we're going to utilize with this a stator field around the outside that's going to give us a complex magnetic field control to give us the motor or generator as we so desire. Now, we're going to provide propulsion, positive flow, forward motion, positive torque, forward motion. This is when we drive the vehicle. This is the first job of the traction motor. As you notice as we go through here, we're going to call electric motors motors, internal combustion engines, and just kind of keep them straight. There is a point in time we want to go in reverse, or if we want to use the forward momentum of the vehicle to generate power to recharge the battery, we use negative torque, negative reverse motion. Sometimes confusing, but you'll see more why when we get further into this. Sometimes we want to have zero torque. In some applications, the drive motor has to rotate. In fact, in all applications, it has to rotate anytime the vehicle's in motion. Now, the ICE will be supplying the propulsion. And again, ICE is internal combustion engine. It is an engine. So it's going to be supplying the propulsion to move the vehicle. And all we're going to be doing with the motor is letting it coast. Regenerative braking is just the opposite. We're going to turn into a generator. We're going to use the forward motion of the vehicle to generate electrical power. You're going to find out this is really significant. Now, here's what a motor looks like. It's got a housing. The rotor you see there inside it, then we have the stator. The stator's a bunch of coils sitting around this rotor. And you see the magnets all buried down inside that rotor. It's going to go around the outside of the stator. Let me say it again. The rotor is on the outside of the stator. Yeah, I know that seems a little strange, but it works very effectively. That lets us put the magnets inside and built a solid frame around the outside to keep the magnets from being forced out of their position by centrifugal force. They're held in position by centrifugal force. Now, to make that motor work, we're going to have this thing we've been talking about, a power inverter. It's going to get information from vehicle sensors and the PCM and everything else. And when you step on the accelerator now, remember, you may not be commanding the internal combustion engine. You may be commanding the power inverter to start supplying power to 3 windings. We call them field windings here because you guys are familiar with field windings. They're far more sophisticated than the field windings on an alternator. But we're going to have 3 current sensors running the output of insulated gate transistors. They're very specialized, high power, high current, insulated, high voltage transistors. Here's the actual thing, the way it looks. At the bottom down there, we have 3 of these high power transistors. In the top, we've got 3 in the bottom. There's 6. Each winding, the U, V, and W, is connected to one pair, a positive and a negative. So what you have is not just one set of windings. Look at the W windings. They're highlighted in red. There's 4 of them. And then 120 degrees away is a similar U winding. And you have to take each red and look 120 degrees, and you find a U. Gets to be a very complex arrangement. Then we have a V. The V's are 120 degrees from the U's, and you have to skip over one to see how they all hook up. What we've got is a whole group of magnets down in the middle, rotating, and these coils outside the magnets supplying all of this force. Now remember, this is inside out. This drawing looks like the coils on the outside. They're not. They're on the inside, and the magnets are around the outside. But this is a good way to represent it. It's too complicated to show you the other way. How does it work? Well, let's look. For this one coil, we're going to have current flowing from the coil to the positive terminal of the battery. And it goes through one of our transistors to the battery. Now, if we had a similar situation for the same coil, we're going to try to go from the negative pole of the battery over to have current flow go into there. It goes the opposite. It uses the transistor at the bottom. So what we're showing you is that the transistor at the top handles one polarity, transistor at the bottom handles the other polarity. We have alternating current. It changes direction from positive current to negative current. We do it with 6 transistors, each pair controlling one coil on the right. So we have all 3 coils working at the same time. Now let's talk about why we have electromagnets and so forth. We are going to be attracting, as you see here. We have a north and a south pole. It is north and south because current is flowing at the top of the coil. And it's going to be attracting that south pole up there. At the same instant in time, we're going to have a coil going in another coil in the opposite direction, and it's going to be a south pole, and it's going to have a repulsion, pushing that away. In reality, like we said, with the UVW windings, we have 3 of them going on at the same time. Now, this is a very simplified view. We're showing you a negative, we're showing you 6 magnets, 3 at the top, 3 at the bottom. In reality, they're all located in one place, and we don't use a bar magnet like you see here. We use a very specific magnet that's U-shaped, like you saw in the actual program. But let's look at this. Let's take a look at current flow. Here we have current flow going in. Right now, that's under attraction. Then we have current flow going out. That phase is on repulsion, and so is the other one. So we're controlling the direction of current flow and reversing and changing the poles to cause attraction and repulsion. This is how the 3-phase motor works. Now, because of this, here's the key. electric motors come up instantly on full torque. Notice the torque right here goes all the way across to 1200 RPM. And we'll talk about why 1200. But as soon as we are ready for forward motion, we hit this with current flow, we have maximum torque. This is very much different than the internal combustion engine. The internal combustion engine doesn't peak out its peak torque till somewhere above 2500 RPM, depending on engine design. You set your peak torque out there someplace in distance. You use a transmission to gear down the speed of the motor initially to give you high torque. We don't need that. What's the best example of this? Is a locomotive. A locomotive has 37,000 horsepower. Yet, when you take that 37,000 horsepower and you apply it to the electric motors underneath the engine through a generator, it starts off at maximum torque and starts that whole giant heavy train moving. As it gets moving, we go to a new phase. Right here, we have torque going down. So torque falls off as speed increases after 1200. But remember, we're out of the startup mode now. We're moving down the highway. But look what happens to power. Right here at this point, horsepower is torque times speed. And because speed is continuously increasing, it offsets the difference in torque, and we wind up with constant power. At cruise speed, we need power. At startup, we need torque. We can take an electric engine that gives us maximum torque at zero and takes us all the way to 12,000 RPM, which is what we need without having to have a transmission. Very important aspect of this. Now, all of this relies on motor control. And we're going to have several motors in this hybrid. We've got to talk about them. Sometimes Delco calls it the machine controller, controlling the machine. The Prius call them motor generators. We'll call them motor generators because it can be both motors and generators, and we'll explain that to you. And in Toyota, they're referred to as motor generator 1 and motor generator 2. Each has a special function. Motor generator 1 controls the planetary gear set and recharges the high voltage battery during cruise. Now, the planetary gear set, in effect, the way it works, gives us a continuously variable transmission for the ICE. It gives us a direct drive for motor generator 2, which is our traction motor. The motor generator 2 supplies the drive power to the wheels at low speeds and becomes a generator doing regenerative braking. And it can come on and help assist the ICE during high demand for power. One thing I use as a key to this is 2 is bigger than 1. The motor generator 2 is a big motor. Motor generator 1 is a small motor. To make them work, we've got to have these power inverters. We've got to have something that changes the high voltage DC from the battery pack to AC voltage to operate these three-phase motors. It's the power from the high voltage back into the hybrid is what we're trying to do. It's the pack for the hybrid system. It controls the power for regenerative braking back to the battery pack during negative torque for regenerative braking. Very complex. We'll explain it to you. You'll understand it. Here are 2 generations. The older one is in the center. The newer ones are on the left and right. On the left, we have it closed. On the right is open so you can see what's inside it. Its function is phase voltage is controlled to set the desired current levels. Phase voltage is controlled. Phases, not its AC phases, positive phase, negative phase. Phase voltage is controlled to set the desired current level. The current level is what controls torque. We'll explain this more as we go along. We need a computer or a microprocessor to determine when the stator magnetic flux level and its frequency. We're going to talk about frequency because frequency is going to be important to us. But we're going to control the timing of this. This is called the desired slip frequency. What happens is, frequency is going to determine motor speed. It is a function of the number of three-phase coil sets we have in our motor. And we're going to find out other things about frequency. frequency multiplied times the number of coil sets will give you RPM. Now let's go back to the beginning statement to make something clear here. We're looking to set the desired current level. The current level controls torque. The frequency put out by the computer multiplied by the number of coil sets is going to return engine speed. We know what it's doing. The computer's smart enough to know how fast the motor's turning. So at 0 RPMs, it can hit high currents, which gives us super torque, and we start building RPM. We don't need any RPM. With an internal combustion engine, we'd have to have it up and running and doing well before we got any torque. Not so. Let's look at this voltage control. The controller uses voltage steps to control voltage, which we call a modified AC signal. The length of time it stays up to that high part of that porch determines the amount of current flow we're going to have. Let's look and see. Notice where the red arrow is pointing. It's pointing over here. That is when we turn the voltage on to cause the positive maximum voltage. And we say max plus voltage. The max voltage is determined by a number of factors. What size batteries do we have? What's the voltage we're using? It will go up to system voltage for whatever it is. This is for the red half of our sine wave. The blue half of our sine wave down here is the opposite polarity. We had positive current flow. Now we have negative current flow. And it's again going to be equal to the highest maximum voltage we have available. We have a true AC, we have a modified AC waveform as you see here. It goes up to a peak and down to the bottom. It is distorted slightly. It's not smooth like this. Those front porches on the positive and negative, how big are they? How wide are they? Determine the amount of current flow we're going to have. Now we said we have 3 phases. They're 120 degrees apart. This is a test of your eyes. Pick the red. That's the W phase. It's a standard sine wave. Then we have the V phase, which is blue. It's a standard sine wave. What you see is when green is high, blue is low. When red is low, green is high. Green being the U phase. What we wind up with, a 3-phase motor, is 3 times as many peaks for our switching transistors to cover. And remember, 6 transistors, 2 pair, 1 pair for each of these 3 sets. So we got 6 transistors turning off and on to control all 3 phases of this. This winds up giving us a 48% increase in efficiency over a single-phase motor. 3-phase motors have a 48% increase in efficiency. Big deal. This is what happens. We have this magnetic field, and it's controlling and modifying this rotor sitting in the middle. We're forcing it to go, in this case, in a counterclockwise manner. Now, the size of the arrow, how big it is, that's determined by current flow. The speed of the rotation of this is determined by frequency out of the electronics. Let's increase the current flow and watch what happens. We bump the current flow up, we have a stronger magnetic field. But look, it's going the same speed. The torque as the motor is increased as current flow is increased. And with torque, we know we're going to get more speed. So as we need it, the computer is going to increase the speed by changing the frequency. Now that we've seen how torque is increased with current flow, we need to talk about how we can increase speed. Now, of course, when we apply torque, we're going to start the wheels turning. The electronics is then going to look at the speed of the vehicle and decide when to increase the speed of the engine. It's going to change the frequency of the drive signal. So now we have our higher frequency drive signal with high current. We're getting high torque and increasing the speed. And as the vehicle goes along, we continue this progress. So let's go back and talk about some of the things that's happening in this electric motor. There's a lag between the stator and the rotor as we go to pushing current through the electromagnet. It's caused by the inductance of the coil. You've all looked at it. You call it current ramping. You look at the ramp, and as you turn the current on an ignition coil, it goes up at an angle. It doesn't start instantly. It takes a time to rise. Now, the controller is going to compensate for this lag by timing this lag just the same way a PCM advances ignition timing, by advancing it ahead of where it should start under normal situations. So let's take it now to a generator and talk about regenerative braking. The power inverter is the mechanism that does this. It changes the motor into a generator by changing the timing of its signals. We're going to use the forward motion of the vehicle as the driving force, and the major change is going to be done with software, because the software is complicated. It's not just running the motor. The hybrid controller now has to talk with the electronic brake controller and decide what percentage of braking is going to be done with regenerative braking and what percentage is going to be done with friction braking. Applying your foot to the brake does not directly apply friction material. It tells the computer how much brake you want, and the computers start talking among themselves to determine the value. Now, during negative torque, the battery pack still has to continue to supply power to the stator, the electromagnets. But the forward motion of the vehicle causes circuit voltage to increase because it's being opposed, and voltages increase sharply, which recharges the battery. Now, an AC inverter is used to power the three-phase traction motors on all hybrids, and some accessories like the AC compressor. Here's our AC compressor, set it off to the side. It has an AC inverter, three-phase, and has a three-phase motor. Remember, far more efficient to have a three-phase motor. This is a good thing. So here sits our AC inverter on top of our AC compressor. Notice that the inverter is almost bigger than the compressor. That's because of the temperature involved here. Compressor gets warm, and so we need a larger area for this inverter to sit on top. So our hybrids are all going to use these AC inverters in the term of vernacular of Toyota. It's going to use it for motor generator 1 and motor generator 2 traction motors. Here's one that's going to be used for an assist motor. So no matter what kind of assist motor we have, whether it's a battery starter alternator or it's one like this between the transmission and the engine, they're all going to have to use an inverter because they're all going to use three-phase motors. Now you can see all the coils in this one and how close together they are. But let's talk about this inverter, and let's get down to talking about exactly how it's going to do it. This particular inverter is used by Ford, Toyota, Nissan. It's not used by Honda because they don't need a boost. Strong hybrids have more cells in their batteries to get a higher voltage than the medium hybrids, or micro hybrids. But strong hybrids are also going to boost the high voltage to even higher voltage levels. Let's take a look at how it does this. DC to DC converters are important in the electronic systems we're talking about, and they're going to be used to replace the alternator. And now the switch DC to DC converter can offer a method to increase voltage from a low battery voltage to a much higher voltage, or decrease high voltage to run a 12-volt system. And DC to DC converters can convert one DC voltage level to another. And they do this by storing the input energy temporarily and then releasing them as a different voltage. It's going to use either magnetic field storage, inductors, transformers, or electric field storage like capacitors to do this thing. Now let's look at the circuit here. We have two switching transistors, and you see a big coil we call a reactor. You all know how reactors work. We look at a primary ignition system. When you stop current flow, the voltage spikes way high. Well, what if we did that fairly often and caused this reactor to charge up that capacitor and then to store that higher voltage in this large storage capacitor the arrow is pointing to here? We take, in this example, a Toyota takes a 288 volts DC and turns it into 650 volts DC. This is a real world. We can read this all in scan data, and as you keep hearing, we keep telling you about scan data. We can read the boost voltage in scan data. We have much higher voltage, we need less current to get the same power. This is what it's all about. Now the DC is then changed to AC, three-phase, and runs the motor at 600 volts AC. So we're running over here at 600 volts AC because we put 650 volts DC in. 650 is, and we're going to now change it. And let's talk about how we've seen those changes made. Now here is a Honda that doesn't have boost. And it's going to be a simple AC to DC inverter. It's going to use 144 volts AC to drive the traction motor. This is a medium hybrid. Doesn't have as much power. But the inverter will control current in the motor coils to generate strong magnetic fields to act with the magnets embedded in the rotor. That's the fundamental way all of them work together. But let's take this a step further. We got 3 coils down here. It's got to control the current in these 3 coils in the traction motor and do it in such a way as it must change the motor to a generator for regenerative braking. Now to do that, we generate negative torque with the forward motion of the vehicle. The major change is done in software. But don't think this software is simple. This software has to talk with other computers and decide between the hybrid computer and the electronic brake controller who is going to handle the percentage of braking. When you put your foot on the brake, does not mean you're going to apply friction material. It means you're going to have the computers to determine how much is going to be done by friction and how much is going to be done by regenerative braking. And that's all based on the speed of the vehicle. We'll go into more detail on that later. But during this negative torque, the battery packs are going to continue to supply power to the stator, the electromagnets. But the strong opposition to forward motion caused by the vehicle will cause the stator voltage to increase since the motor is acting like a generator, which is now going to be used to charge the battery. And a microprocessor controls all the transistors and diodes in the power converter for this regenerative braking. We're going to see exactly how this works, but we've got some limitations here. If the battery system is fully charged, the power pack controller signals the power inverter controller to eliminate negative torque, and regenerative braking will stop and give all the braking 100% to friction. Let's look at how this regenerative braking is going to recharge the voltage. As we use the forward motion to force this generator through its generating cycles, the AC voltage by regenerative braking is changed to DC by these diodes beside the switching transistors. The blue up and down arrows are your AC voltage. They go through the diodes. They become positive voltage at the top, negative voltage at the top, go back and recharge the battery. And you're going to find out this is a significant amount of power. Unbelievable amounts of power we're talking about when we do this. Regenerative braking takes place when the throttle is released. It takes place when the throttle is released or the brake is depressed. Either way. The hybrid controller determines the percentage of friction and regenerative braking to be done. And then it relays that information to the electronic brake controller. The brake pedal pressure and position is measured as part of the inputs of this section. Friction brake is then controlled by the electronic brake control module, which communicates back to the hybrid controller to make sure we're getting the deceleration we're anticipating. And we're going to cover all this later, and we'll show you all the solenoids and the electrical side of how the brake controller works. But in order for the microprocessor to do all these things, to control the motor, to control it into a generator, we're going to have more information. Most hybrids use a resolver attached to the rotor to detect a few things. We need to know the motor direction, the angular position of the motor. Exactly where is it positioned? Because in different positions, we need to have different electromagnets turned on. Then it's going to have the RPM of the motor. Take these 3 things and we can make it a motor, we can make it a generator, we can increase speed, we can increase torque, whatever we need to do. They can be designed to have any number of poles. The more poles you have, you'll get better resolution. Resolvers send the inverter controller information about motor direction, position, and speed, as we've said. It uses a sensing element and a reluctor to create signals. Remember how reluctors worked in our electronic ignition? Magnetic coupling. Now, the number of lobes in a reluctor will determine the resolution. And we have a couple of them to look at. This is a 4-pole reluctor, meaning it's got 4 lobes. This one has about a dozen different lobes, and this one has 2. So we can have any number. Now here's the one that has about a dozen. It's located back behind this bearing. As we look down inside, you can see the pickups. Those are all different parts of the pickup for this resolver. Very high resolution resolver. The resolver is attached directly to the rotor. It rotates as the rotor rotates. So it tells us where the rotor is. Where the rotor is tells us what to do with our electromagnets. Let's take a look at this up close. We have an excitation coil called coil A. It creates a magnetic field that is then detected by the other coils. The mover and reluctor causes the signal amplitude to change as the rotor rotates. Now, as you can see, we have close proximity between coil A and B, and coil C is out with no contact with the reluctor. So the voltage induced at this time will be higher in coil B than it will in coil C. Here's what happens over time. Coil A is the frequency at the top, and then we have 2 at the bottom highlighted. Coil B is going to be just the opposite of what we're doing in coil C. When coil A is exciting these 2, the amplitude of coil B will be going down when the amplitude in coil C is going up. That's those 2 highlighted in the middle. We've got 2 on each side. So what this tells us is exactly the position at all times. And the computer can use these high-speed signals in a few milliseconds to know the exact position of where the magnets are located and what to do with the electronic switching. So all this electronic switching all comes back to this right here. What is this doing? Where's the position? Once we know that, we know which coils to turn on. Now, once we decide to turn them on, we're going to drive current with voltage, and we're going to control torque, so we're going to have to measure the current flow. This is going to tell us the delivered torque. We're going to see scan data that says desired torque, delivered torque. How do we know how much torque is delivered? Torque is delivered by the amount of current flow can be calculated. It's used also for diagnostics. Here's one that's completely removed so you can see this is a double-ended one. Here's one in place. I want to show you a few things here. This is one side of the Hall effect current sensor. Let's take a look at the other side. On the other side, we notice we have a voltage sensor. What you're going to understand, in our next class on hybrids, we're going to get down to the nitty-gritty of all these different voltages and currents that are being sensed inside these controllers. And the reason for doing that is so that you never have to come in here and put a voltmeter where that voltage sense lead is right there. You'd have to have rubber suits, rubber gloves, safety materials in order to get into this inverter and go there. You have one of these on each one of the coils going to the motor. So we can watch the current in each of the coils and diagnose it from scan data without exposing ourselves to the dangers of this 650 volts in this particular case. We also are going to have current sensors out at the battery blocks. And we're going to talk a lot about, we've talked a lot about battery blocks. There's 2 bricks in a block. And we have to reduce it so every other battery has a voltage sense. It reads the voltage for 2 batteries. These are going to be used for diagnostics. This is how they attach to the batteries. Notice one side of the battery's got one lead. The other lead's on the back side of the battery. So these are all going to be used to link all these batteries in series, and all these little small wires coming off those sense leads are scan data leads right there. So we have a lot of scan data. The high voltage, that's the big orange leads. So we've got little leads measuring the voltage. We've got big leads taking the voltage out, ready for 100, 150 amps current flow. We've got to manage this because of current flow. We can't let it go unprotected. So we have fuses out here that'll terminate battery power, open the circuit, whatever you want to call it, in the event of a catastrophic failure with excessive current flow. Now they're located in these safety switches. The Ford over here has a 200 amp fuse. The Toyota on the other side has 125 amp. So we got 200 amps, 225. We're looking at 300 volt power packs. These are tremendous. We're talking 60,000 watts on the Ford is the maximum possible we could see. 60,000 watts. The average house is wired for 22,000 watts maximum, and this is set up for 60,000 watts, almost 3 times as much as a house. So we keep harping on respecting this. It's really very true. So here's how things are going to work. We got different battery blocks. On the bottom we got blocks 1 through 19. The top we got 20 through 38. In the middle we have a fuse and a quick disconnect. They're married together right inside here. What you're looking at here is right inside that quick disconnect, our manual disconnect switch. So those in the white area are all inside this orange manual disconnect of this Toyota. Scan data is used to measure the voltage at all the fuses at all of these points. We keep telling you, scan data, scan data, scan data. We're going to beat you to death with scan data because it keeps us from exposing ourselves to the high voltage risk. Now we've got to control the thermal activity. We cannot have the battery be too warm. We got 2 types of temperature: ducted ambient air, called passive cooling, and fans along with air conditioning, caused active cooling. The arrow here is pointing to a vent. That is just standard passive air. It's ambient air being allowed to drift through. But ambient air is not enough. You'll find we have big fans. There are 2 cooling fans on this cooling pack that we've opened up. Here's a bigger pack that has 3 cooling fans. And here we have an evaporator. Look over on the left side, right here. Here's the battery evaporator. This happens to be off a Ford Escape. What happens if the computer determines, the hybrid controller determines that the battery pack is getting warm? It will start the AC compressor, which in this case requires that the ice starts up as well. It's going to run the air conditioner and cool down the battery pack, even though the passenger has not selected air conditioning. It's going to run the air conditioning because the batteries need it. It will do anything necessary to protect this battery pack. Liquid cooling is one way we're going to protect it. Now at the bottom is the IC engine. It's got a thermostat, and it's got a storage, high temperature storage container. But just imported above that is one without any thermostat. It's circulating cool water through a radiator to keep the motors, the generator, and the power buses and inverters and all of that cooled down. And we've got an AC condenser up there, and finally there's another grill. So we got 3 radiators for this to go through now, not just 2. And that's important. The battery control system is going to monitor the high voltage battery temperature closely because it's part of our requirement to make our system last longer. It will go to any length to keep the high voltage battery pack from overheating, even shut down the entire vehicle. Here is an example of one sensor. Just above that, just about out of sight, is a second sensor. Let's take a look at 4 of them. We had to take 4 different photographs to get the battery pack across all the way across. There's one at the end, one on the left side, one on the right middle, and one on the right side as we look in from the back. 4 different temperature zones, trying to make sure we know what's going on. We even have coolant storage that stores coolant in case the internal